So that will be like and in the last scientific lecture, we studied about the autoregressive model, right? And
Can't hear you.
yeah. So we started off with the AR1 model. That we know that when I'm talking about the AR model, which is the autoregressive model, I'm just regressing my XT on its past values, which is XT.
I can't hear clearly.
Yeah, thank you. Can you hear me better now? Yeah.
Yeah, better.
Hello. Am I audible?
Yes, ma'am.
Okay, was I audible up until now?
No.
No. Oh, okay, so let's start again. So we started off with AR model, right? And I know that when I'm talking about AR model, it is just an auto-regressive model where what I do is I regress my XT here upon its
Ma'am, you're not
Can't hear.
audible.
Am I audible now?
Yes.
Yes.
Okay, I don't know what's happening, but yeah. So what I was saying is, I know that I can always write my XT in terms of ease. So if I want to figure out whether my AR process is a stationary process or not, then what are the conditions that should be satisfied? Can someone tell? Hello, am I audible now?
Yes.
So now you can hear me, right? Okay. So what I was saying is, what are the conditions that should be satisfied for an AR process to be a stationary process? Anyone?
Mean and variance should be constant.
Yes, mean and variance should be constant and
The covariance should
Correlation should
be on the lag.
We can't hear you.
uh, can everybody hear me?
Yes, ma'am.
yes.
Okay, fine.
Yes.
Okay, thank you. Yeah, so we want mean and variance to be constant and we want covariance to be independent of the time period, but only dependent on the lag. So we solved and we got that an AR1 process is stationary if the coefficient of xt minus 1 here is less than 1 in absolute magnitude. So if this is less than 1, I know that my variance is going to be a constant and my mean is going to be a constant when my mean for each and every time period is just mu, which is the constant term that I have up there. Okay, so that was for AR1. And then we figured out its covariance and stuff. So after which we looked at an ARP model and we figured out the conditions for ARP model to be a stationary model, which turned out to be that all the roots of its characteristic polynomial, which is derived from this substitution of backwards shift operator instead of this x is here, which you take as common for xt. And then these roots of this characteristic polynomial should be greater than 1. They should be greater than 1, not equal to 1 or neither less than 1. So, and then we looked at, how was that condition derived intuitively, not exactly. But yeah, I guess you got the gist of it. So the next step we did was we figured out a sum on how to, claim if a model is stationary or not. And then we looked at another problem where we figured out how to calculate this autocorrelation. So we saw that the very good technique to figure out autocorrelation is, because we know that to calculate autocorrelation, we will require the autocovariance. So we take autocovariances with no lag, with 1 lag and with 2 lag, because we only have up until xt minus 2 here. And we write gamma 0, gamma 1 and gamma 2 in terms of each others. So when you substitute this, we do not sit and solve for this. We instead just write it as gamma 1, gamma 2. And we have this, so essentially we don't use this equation, but we have these two equations in 3 unknowns. So we write gamma 1 and gamma 2 in terms of gamma 0, and we substitute those terms back in here to get the value of gamma 0 in terms of sigma square. And once we have that sigma square value, so you can easily get the value for gamma 0, gamma 1 and gamma 2 in terms of sigma square, which will eventually help you to figure out the partial autocorrelations. So we'll have a look at another example today where instead of figuring out the autocorrelations separately for lag 1, 2 and 3, we will see if we can devise a function for the autocorrelation function, which will be a function just of k. So that if you have to figure out autocorrelation for lag 1, you can just substitute 1 instead of k in that function and you will get the answer for your autocorrelation. So another example, and for this we are going to have a look at a AR2 process, which they have already mentioned is a stationary process. So you do not have to check whether this process is a stationary or not. Okay, and the question asks us to figure out a general form for autocorrelation function. What should I start with? Any ideas from anyone?
Covariance xt and xt plus k.
Covariance xt and xt plus k, right? Okay, so let us see. So that is going to be our first guess. I mean, that is not a bad guess, I would say. So you have to figure out rho k. So rho for any k, right, is what you want to figure out. So what first comes to your mind is, let us figure out the covariance between t and t plus k, and then I can just divide it by the gamma 0, right? But then would it be a function of k? So if you have gamma 0 in the denominator and you're thinking that, at the end you want this to boil down to a function of just k. So you will have to eventually figure out what is the value for gamma 0, right? For that. So there is another method that you can use. So let me just show it to you guys and then you will see how does this help us to get to, what we are looking for. So what I will do is I'll use the same thing that we did in the previous question. Figure out first gamma 0, which is what? Covariance of xt with xt itself. So I'll have covariance of xt minus 1 5 by 6 minus 1 by 6 xt minus 2 plus et comma xt. So if I were to write this again, I can easily write 5 by 6 and covariance of xt minus 1 comma xt will just be gamma 1. Similarly, I'll get 1 upon 6 gamma 2 here. And now I have to figure out the covariance between et and xt. So instead of xt, I substitute all of this. And we know that this term wouldn't matter. Neither this term would matter. But again, just for the sake of it, let me write it again. So if you figure out this value, it will just be covariance of et comma et, which is nothing but the variance of et, which I didn't mention, but is sigma square. Okay, so what I get here is that my gamma 0 is equal to 5 upon 6 gamma 1 minus 1 upon 6 gamma 2 plus sigma square. So this is one equation that I have. Now let me try to figure out gamma 1. So I hope you all can figure out gamma 1 and tell me what the gamma 1 value will be here. Write it down in your notebooks and tell me what should I write for gamma 1 there.
Covariance xt comma xt minus 1.
Yeah, and I want the final answer in terms of gamma 0 and gamma 2, if there will be gamma 1, gamma 0, gamma 2. Final answer.
Anyone?
5/6 times gamma 2
5/6 times gamma 2
minus 1/6 times gamma 3.
minus 1/6 times gamma 3.
Yeah, that is it.
That is it. Okay, so let us try to see how will I write my gamma 1. So I want to write my gamma 1, which will be what? Covariance of xt comma xt plus 1, right? Or I can also write it as covariance of xt comma xt minus 1. So if I write it as covariance of xt comma xt plus 1, and if I expand my xt, what I get is 5/6 xt minus 1 minus 1/6 xt minus 2 plus et comma xt minus 1, right? And if I write it as xt plus 1, and you will get the answer what Sakshi just told us, right? So you will have 5/6 gamma 2, which is exactly the difference between xt minus 1 and xt plus 1. And you will have minus 1/6 gamma 3, right? And now let's see what happens if you write covariance of xt comma xt minus 1. So if I have to write covariance of xt comma xt minus 1, I'll again expand my xt. And what do I get here? So I get my gamma 1 as something. So here I have xt minus 1, and here again I have xt minus 1. So I'll have 5/6 gamma 0 minus 1/6 gamma 1. And you know that this is indeed an even function, right? So this would eventually be gamma 1, but I know that this is always equal to gamma 1, right? So what do you guys think? Should I use this gamma 2 and gamma 3, or should I go with the term where I get gamma 0 and gamma 1?
Gamma
Which
0 and gamma 1.
equation? Right? So I know that because I'm having one equation already with gamma 0, gamma 1 and gamma 2, it would only make sense for me to have another equation which is for gamma 1 in terms of gamma 0 and gamma 1 instead of gamma 2 and gamma 3, which is just, adding to the variables that I'm considering. So not every time you will have the advantage, of either using this or that. So remember in the previous question, even though in the answer book it is done in the other case, I have deliberately shown on the blackboard doing xt plus 1 case. But here, I can clearly see that if I use xt plus 1, I'm getting something as gamma 2 and gamma 3, which clearly does not help my case here. So I will resort to not using this equation and instead go for xt minus 1 here. So instead of xt plus 1, I'll choose xt minus 1 here, which gives me a very good equation right here. Okay, so now if I have to figure out gamma 2, what should I do? I should again write covariance of xt comma xt minus 2. And can anyone tell me the final answer like this for gamma 2?
It'll be 5/6 gamma 1 minus 1/6 gamma 0.
Does everyone agree with that?
Yes.
Yes, ma'am.
5/6 gamma 1.
So, yeah, this was gamma 1, right? So we have these equations, and now you know what kind of structure do you have to, keep in mind when you're trying to figure out these values. If you are, to figure out these covariances. And now you have 1, 2, 3 equations and 3 unknowns, gamma 1, gamma 2, and gamma 0. And you can easily figure out the value of gamma here. But remember, what we have to do is, instead of looking for this kind of a case, what we are asked to do is to figure out a function for our autocorrelation. So let me take these. So what I will do is, I will use this equation here. And if I know that, let me just write it there. So if I have to figure out rho 2, so if I have to figure out rho 2, it will just be gamma 2 upon gamma 0, right? So what I will get here is gamma 2 is what? It is just this. So I can write my gamma 2 as 5 by 6 gamma 1 upon gamma 0 minus 1 upon 6 gamma 0 upon gamma 0, right? So what I have here is that my rho 2 is equal to 5 upon 6 gamma 1 upon gamma 0. So how can I write my gamma 1 upon gamma 0 as?
Rho
It
1.
can just be 5 upon 6 rho 1, right? And this is just 1. So this is minus 1 upon 6. But I know that 1 is what? 1 is just rho 0 here. So I write rho 0 here. And we always know that, and we know that rho 0 is always 1. So I get my rho 2 as something which is 5 upon 6 rho 1 minus 1 upon 6 rho 0. So if I were to write a function for rho k using this equation that I have there. So let me just copy that. Yeah. So I have this equation right here. And if I were to write an equation for rho k using this, I know that I have my 5 upon 6 here. And this is what? 2 minus 1. So rho k minus 1. And here I'll have minus 1 upon 6 rho k minus 2. So this is just a very haphazard way of, writing this equation. Rather, what you should do is figure out the covariance for k, and then you will eventually get the same answer which I have written over here. So that's how you get this equation right here. And now what we have to do is, this is just a second order difference equation. And if you look up in your table booklet, so because I know that this is the only random variable I have here is this rho here. So rho k minus 1, rho k minus 2. And these are at different time periods. And what I have to figure out is the value of rho k. So if you open your table booklet and go to the page where go to the page number 4. Let me know once you have page number 4. So, or maybe I can just, write a short note here. So, second order difference equation. And so this is the formula that we are going to take into consideration for this case. And so the equation, the general solution is this, and the equation for this is given in the book as ax n plus 2 and this should take the value 0. Okay, so now if I were to compare this formula that I have just written on the board with the equation that I have. What do I get? I'll first have to figure out the lambda 1 and lambda 2 for this. So what I do is, this is my second order difference equation, and I'll write a characteristic equation for this, which would just be, so if I just take all of these there, I know that here I will get lambda square minus 5 upon 6 lambda plus 1 upon 6, and this is just equal to 0. Do you understand how I got that? Does anyone know how did I just derive this characteristic equation? Can you try to derive a characteristic equation for this?
So you use the row values as variables and then derived it using the general form of the equation.
No, but my question is, how did I get the characteristic equation in the first place?
Backward operator.
Yeah, can you show me your working for the backward operator? Because this is really the most important part.
You took rho k out common, I think.
See if that works out.
No, wait, 1 second.
Rho k minus 1 will be b times rho k, and rho k minus 2 will be b square times rho k.
Yeah, and if I do that, I should have lambda square for 1 upon 6, right?
Yes.
So what I am doing is, I'm shifting all of these k's by 2. So I have rho k here, and for this k, I have this function right here, but I have k minus 2 and k minus 1, and I hate to work with minuses. So always remember, whenever you are at this juncture and whenever you have to figure out a characteristic equation, it's always better to just make all of these terms positive and leave the term which is the least as k. So what you can do is, this will just be equivalent to writing rho k plus 2 minus 5 upon 6 rho k plus 1 plus 1 upon 6 rho k, and equate this to 0. Does this make sense? And then I can easily take my rho k as common, and I will get the same characteristic equation which I have here, right?
Yes.
Is this clear to everyone?
Yes.
Okay, good. So now what we have to do is, we just have to figure out the roots for this equation. And what generally helps is, you just take 6 there, and you can transform this as, and now you can easily figure out the roots, or you can even use the quadratic roots formula to figure out. I don't care how you go and solve that. Just do whatever, feels easier for you. But I'm not going to show that here. So I'm just going to write that this solves as this thing right here. So now remember that I was figuring out the characteristic equation for this row function, and I have my lambda value. So one of my lambda values is 1 upon 2 and the other value is 1 upon 3, which are two distinct real roots. So I will use this formula from the table booklet to now write the answer for this. So what I have here is a lambda 1 raised to 1 plus b lambda 2 raised to n, and here I have xn, and these a and b are just the constants that we do not know yet, which we have to figure out. So I will write here from the table booklet, page number 4. You know that the general equation is going to be something like a times, so my lambda 1 is 1 upon 2, and here instead of n I have k, and then what I have is, so remember, now that I have my function as it is, right, it corresponds to this, so I can easily take the same differential here. So a 1 upon 2 raised to k plus b 1 upon 3 raised to k. So, okay, now we know that a and b are just constants, and we have rho k in terms of k's only. So the only thing that we have to do is now figure out the values for a and b. So what do you think I can do to figure out the values for a and b? Anyone?
K is 0, that time row K is 1.
Exactly right. So what I can use is, I can use the fact, so I will use the fact that I already know my value for row 0, which is always 1. So I'll substitute this in here, and what I get is that my row 0 is equal to a, anything raised to 0 is 1. So this is just a plus b, and I know that a plus b have to be equal to 1. Okay, so this is one equation that I have, but I have two unknowns. So I need one more equation. And what else can I do? I can maybe use the equations that I derived earlier to figure out the value for row 1, right? Which is the same thing that I'm going to do now. So I want you all to use these equations as in how, like, in any ways you can, to give me the value for row 1. So I want the value for row 1 here. So remember, row 1 is just gamma 1 upon gamma 0.
So row 1 will be 5 by 7.
And how did you derive that?
Because 7 gamma 1 is 5 gamma 0. So when you divide both sides by gamma 0,
Right.
effectively it's 7. Row 1 is equal to 5. So row 1 is 5 by 7.
Exactly. So you don't have to do anything. You have it right here within just one equation, that gamma 1 upon gamma 0 is 5 upon 7, which is nothing but row 1. So I also know that my row 1 is just 5 upon 7, and if I substitute k as 1 here, what I get here is a upon 2 plus b upon 3. And what I have to do is just solve this equation and this equation right here to get the value for a and b's. And if you solve those, the answer that you get will be, so for a, you will get the answer as 16 upon 7. And for b, you will get the answer as minus 9 upon 7. And then you can write that your row k is just, so instead of a, You substitute the value that you have here. So you will write 16 upon 7 times a half raised to k plus minus 9 upon 7 third raised to k. And this is the answer that you have. Is this clear to everyone?
Yes.
Yes, ma'am.
Others?
Yes, ma'am.
Good. Shivam, Swapnil, Sakshi?
Yes, ma'am.
Yes, ma'am.
Swapnil?
Yes, ma'am.
Okay, perfect. So that was it about the AR process. And there will be various other sums which will more or less use the same techniques that I have used in these three sums. And we'll do some sums maybe in the next lecture, where you will also have to, carry out the mean of the process first, and then look at, if there is some changes that you want to do in the process that you have, or just something else, but that's for later. So now we will have a look at the another kind of model that you can have, which is a moving average model. So again, right before we generalize it, let us have a look at MA1 model. So if I were to write my MA1 process, it would look like, so this is the mean that I have, and this is the general ET that I have. And now because in MA what happens is, my XT depends not only on today's white noise, but also on yesterday's white noise. And what I do is, I write a coefficient beta for it. So again, what we will do is, we'll figure out the conditions for which this process is going to be a stationary process. So if I have to figure out the mean, what is going to be the mean of this process? Quick
Mu.
answer, mu, right? Because the mean of these two terms is going to be 0. So the mean is a constant. And if I were to calculate the variance, it's again going to be just sigma square plus beta square sigma square, right? Because ET and ET minus 1 are also independent. So that is also some constant, which I just don't know the value of. And now let us try to figure out the covariances. So I know that my mean and variances are constant. So I'll have a look at the covariance now. So stationarity. So the mean is just mu. Variance is just covariance of xt with xt, which is nothing but gamma 0, which is just sigma square 1 plus b square, right? So let me now figure out gamma 1. This will be covariance of xt, comma, xt minus 1. So I can write my xt as, so again I'm not writing this mu because these are just constants and it doesn't matter when I'm talking about covariance. So I'm just writing it as ET plus beta, ET minus 1. So see, now when I was trying to figure out this gamma 1, I knew that I have to take xt minus 1 instead of xt plus 1, because I know that the terms that I will have in xt here are going to be t and t minus 1. So if I have to in a way figure out any relationship, I should take xt minus 1, because if I write xt minus 1, it will have t minus 1 and t minus 2. So for xt minus 1, I will have et minus 1 plus beta et minus 2. And then again, this will just go away, that will go away, and these are the only terms that will remain. So you will have beta sigma square. And now let us figure out gamma 2. This will be what? Covariance of xt comma xt minus 2. And if I expand xt, I get et plus bet minus 1. And for xt minus 2, I get et minus 2 comma plus bet minus 3 and tet minus 20 minus 2t minus 3. So this is just, wow, I forgot to write the covariance here. Yeah, so this is going to be just 0. And I observe that if I take t minus 3 here, I will have t minus 3 and t minus 4. So for all of my gamma, which have a value of k, which is greater than or equal to 2, it takes the value 0. This is a very, very, very important result in time series and also for the next chapter, I would say. Because what happens is, whenever you are given a data, so you always have a sample and you plot its ACF and PACF, and then you decide which model are you going to use. And now you know that for any MA process, so now we are doing it just for MA1, but this is true for any MA process with any order, be it 1 or any other number, that its covariance function after its order. So if I have my order as 1, then for any value of k which will be greater than or equal to 2, or for any k in fact greater than 1, my value for autocovariance is going to be 0, always. So you know that if you plot a ACF, so let's say you plot a ACF and this is your sample, so this is your lag, so you will have lag here and you get some value here and you get some another value here and then you get no values here. So you know that this process satisfies MA of what order?
1.
1. So this is k equal to 1 and this is k equal to 2. So if it is this, then it will be MN2, right? And generally, if you start with 0, so it's always, better to start with 0, and that is how you will get in terms as well. So if you have k is equals to 0 here and k equal to 1 here, then this will be MA1 process. So this is 0, 1, this is MA1 process. Okay, so now we know that for any MA of given order, I know that my autocovariance for any lag which is higher than that order is always going to take a value of 0. So let us now try to figure out what happens with the autocorrelation. So I know that this is again stationary, right? Because I have my covariances, which are just some constant numbers, right? And again, we'll see it again, when I generalize this case, that MA process will always be a stationary process. Because you know that it is nothing but just a linear combination of some white noise processes that I have. So it is always going to be stationary because any white noise process is always stationary. And that is why you never have to worry if your MA process is stationary or not. But there is something else that you have to worry if you are, dealing with the MA process. And I'll show that to you in a while. First, let us derive the autocorrelation. So if I have to figure out my rho 0, what will that be? Will this be 1 again for MA or can it be something different for the MA process?
It will be 1.
It will be 1, right? And why do you think it will be 1? So because even though I have a MA process, this is just going to be my gamma 0 upon gamma 0, which irrespective of what process I'm looking at is going to take the value 1. Anything upon itself is just 1. So again, my rho 0 here will be 1. So let us now look at rho 1. This is nothing but gamma 1 upon gamma 0. So gamma 1 is what? Beta sigma squared. So I write beta sigma squared. And what is my gamma 0 here? Sigma square times 1 plus beta square. So these and these will cancel and I'll be left with a beta upon 1 plus beta square. And now if I have to figure out my rho 2, that will be gamma 2 upon gamma 0. So I know that. What will be the value for this? Anyone?
0.
Why do you think it's going to be 0?
Gamma 2 is 0.
But what is the guarantee that gamma 0 is not also 0? Because it can be 0 upon 0 as well, right? Indeterminate. Oh no, there's no minus. We have 1 plus beta square, right? So gamma 0 can never be 0 because anything squared is going to always give you a positive number. So this will be 0 because the numerator is always 0, right? So I know that for any k which is greater than 1, my rho k is also going to be 0. Is this clear?
Yes.
Perfect. So now I will tell you guys why do we have to, not worry about stationarity but something else whenever we are faced with the MA process. So now I'm looking at my two MA processes where one is and the other process. So I want you all to figure out the value of gamma 0 for this and gamma 1 for this guy. And again, figure out the value of gamma 0 and gamma 1 for this guy. And then rho 1. And then so what will be the value of gamma 0 for the first case?
Beta square into 1 plus sigma square.
So it will be 1 plus beta square times sigma square, right? And gamma 1 will be So this is actually the same case as the previous one, which is solved, right? I have just not written mu here, which doesn't anywhere matter for the covariances. So my gamma 1 in the previous case was beta sigma square, and my rho 1 was beta upon 1 plus beta square. So you just have to figure out the values for this case. So what will be my gamma 0 for this case? Anyone?
Sigma square plus 1 by beta square sigma square.
Yeah, and I can write it as this. Right, sigma square, I can take it out as common. So again, you don't have to, even solve this again. You just have to realize that instead of beta, I have 1 upon beta here. So instead of beta everywhere, I can just write 1 upon beta. And that will be your answer. So again, if I were to figure out rho 1, it will be what? Gamma 1 upon gamma 0. And that just gives me sigma square upon beta. This is my gamma 1. And my gamma 0 is sigma square 1 plus 1 upon beta square. So I can write this as beta square plus 1 upon beta square. So beta square plus 1 upon beta square. Does that make sense? So now I cut this and I again cut this, and what I'm left with is beta upon 1 plus beta square. So why do you guys think I gave this exercise to you? What do you see here? What's happening?
Correlation is constant.
It's so instead of constant, you can just say that the correlation is same for both the series. Even though the coefficients of the series are different, they are reciprocal of each other. I know that my autocorrelation function is the same, right? So we know that we can have two MA processes which are completely different from each other, but still exhibit the same autocorrelation function, right? So I can easily write here that ACF does not uniquely determine the process. So whenever I'm given a sample, let's say if I'm working with a time series and I have a data with me, so what I can do is I can plot a ACF or a PACF to check, right? But if I plot a ACF here, I still won't be able to determine just by this ACF if my process is this or if the process is this, right? You can never identify the process uniquely with its coefficients. I mean, you can maybe say by seeing where it cuts off, where it becomes 0, that how many lags will there be in the process, but you can never say or anything about the coefficients, right? Because you know that the ACF can still be same and the coefficients can still be different. So you will get some multiple values for the coefficients that you are looking for. But in actual, whenever you go to any statistical software and you use that, you will only get one value for the coefficient, not multiple values. And that happens because of some property which is known as invertibility. So we'll discuss that now. And we'll also talk about, what do I mean when I say that my MA process is an invertible process. So now I started off with my MA1 process, right? And the MA1 process which I had was something like x equal to mu plus et plus beta et minus 1, and I can rewrite this as x minus u equal to et and 1 plus beta, and this is my backwards operator. Does this make sense? I can write it like this, right? So now if I want to figure out my ET, what I can do is I can apply inverse, and I can multiply and divide that inverse on both the sides. So I will divide this inverse both the sides. So what I will get is, I will multiply its inverse and I will divide this on both the sides. So what I get here is x minus u 1 plus beta b inverse equal to et. Sorry if I have xt here. Does this make sense?
Yes, ma'am.
Good. So now we will do something. Now, how should I, expand this inverse that I have here? What can I do to expand this inverse? Anyone? Any guesses?
Binomial expansion.
But do you know the value of beta? So if I look up the binomial expansion on page number 2 of the table booklet, it has a condition, right? That whatever term I have with 1 should be less than 1 in absolute terms, right? So what we do is, instead of making this valid for each and every value of beta, we just assume, so you assume that your beta is lesser than 1. Then I can use the binomial expansion to expand this. And can you guys do the expansion? So, or should I do it? Or do you guys want to try the expansion? So what is my P here? If I compare it with the formula that I have, my P here is just 1, right? Is it 1 or is it minus 1?
-1.
Right, so it is minus 1, not 1. Good. Okay, so guys, let me take a break for 5 minutes and I'll come back. And by that time, I want you all to figure out this. So I want you all to figure out the value for this expansion. And I'm just going to, show you guys something else. So on page number 662, you have this question here. So I want you all to, try this question. So this is page number 662. I'll see you guys in 5 minutes. Did you guys try?
Yes, ma'am.
So can you put up your answers? And so were you guys able to solve this question?
Yes.
So I hope you all have, just checked your solutions there. So does anyone have problem with this question?
No.
This is actually just similar to what we did, right? Instead of E, there is just a Z here. And what about this expansion? I want to hear this expansion from someone, anyone.
It will be 1 minus beta b plus beta square b square minus beta cube b cube and so on, plus beta raised to 4 b raised to 4.
So you say it will be 1 minus beta b plus beta b square.
No,
Sorry, b
beta
square
square.
beta square, right? So at the end, if I can rewrite this whole equation using this expansion, so I'm assuming that this expansion everyone could get. Is there anyone who had difficulty with expanding this? Well, I'll take that as a no. So I can rewrite this thing as xt minus mu times 1 minus beta b plus beta square b square minus beta cube b cube and so on, right? And then till what power will this go on?
Infinity.
Right, it will go on till infinity. And I will just have here equal to et. So tell me one thing, this et is some finite number, right? And if we want this process, this expression right here, to take a finite value and not blow up. So I know that when I am adding more and more terms, I'm tending till infinity. So at some point, I'm increasing the powers of this beta right here. Even though I'm subtracting beta cube, I am going to add beta raised to 4, right? So that is just going to increase the value of beta that I have, unless I assume that beta is less than 1. So the very fact that we can use this formula is by assumption that beta is less than 1 in absolute value. And this is the one thing that again allows us to say that this series is going to be a convergent series rather than a divergent or anything which is not convergent series, right? So that is what I mean when I talk about invertibility. So when I'm inverting this characteristic equation here, I should be able to invert this function to rewrite my ET in terms of this. So let's say if I expand this now, if I multiply this bracket every time, what will I get? Let me see. So xt minus mu times 1 is just xt minus mu. So this is xt minus mu. Then I have minus beta b. So I will write minus beta, and instead of b, so I know b times xt is what? Xt minus 1, and b times mu is just mu, right? Then I have plus beta square xt minus 2 minus mu, and so on, ultimately equal to ET. And what do you guys think this looks like? So right now, what I have is xt depending. So I can always, take these values on the right hand side and have only xt on the RHS. So I know that my xt depends on xt minus u and xt minus u. till infinity, right? So I know that whenever I'm given a MA1 process, I can rewrite that process only if it is invertible as an autoregressive process of infinite order, because there is really no limit to this. So this right here is a autoregressive process with the order as infinite. I don't know what happened there. Yeah. So it is an autoregressive process of infinite order. Does this make sense?
Yeah.
Did you guys understand what I just wrote? So all I am saying is, so let us revise what all we have, just known up until now. So we know that AR process is stationary if the characteristic roots of the AR process have roots which are always greater than 1 in absolute root value. And for MA process, I don't have to worry about its stationarity. So I know that my AR process is stationary if its characteristic roots are greater than 1 in absolute value, and my MA process is always stationary. But I know that my MA process is invertible if and only if my beta in absolute terms is less than 1, right? And when I can invert a MA process, I know that upon that inversion, I get a transformed process, which is just an autoregressive process of infinite order. Does this make sense?
Yes.
So the concept that we studied here is invertibility. This is of utmost importance. And that happens because we can invert this guy right here. Okay. So now you see that there is indeed some connection between an AR process and a MA process, right? Okay. So next. So there is one important theorem which we don't have a proof of, but we just need to know it, that even though there will be more than one MA processes which can share the same ACF, there will only be, at most, there will only be one process which will be invertible. So either all of the processes will not be invertible or one of those will be invertible. There cannot be more than one process with the same ACF which are invertible, right? So there is only one coefficient that you will get when you invert. So that is how, let me just write it here for completeness. Although okay, I'm not writing it. This is just plain. So you guys get the gist, right? Even though there will be so many MA processes which will share the same ACF, there will be at most one process which will be invertible. And that is the process that you will always get whenever you put your data into a statistical software. So they automatically consider the beta value less than 1 because that is the only thing that is going to make the other side convergent, right? So that's it. And next up, I think,
Hello.
yes.
Sorry, ma'am. Can you please once again explain what is invertibility? If the process
What is invertible?
converges.
Okay, so what I was trying to say is, so just forget that, the binomial expansion works only if beta is less than 1. Forget about that. Let us assume, so this is not true, okay? I'm just assuming that this expansion is always true, right? But I know that I'm multiplying xt minus mu with something which is going on till infinite time. So how can I be sure that it will not blow up? And when I say blow up, it just means that it will not go to infinite. Because I know that this times that should only be e times t, which is some number, right, which is clearly not infinite. So I want this series right here to converge to some number. But I know that I have beta square here. So I'm adding beta square. Then I will be adding beta raised to 4. And at some point, I will be adding beta raised to infinity,
Yes.
right? So to negate the effect that, you are increasing the powers of beta, as in when you add more terms in this series, what you do is, if you want this series to converge, because you already know that this times that is going to be some finite number, so you already de facto know that this is going to be a convergent series. This cannot blow up till infinity, right?
Yeah.
So you want these beta sequences that you have to have a lesser and lesser value, and that is possible if your beta takes a value less than 1 in absolute terms.
Yes.
So what's allowing you to write a MA process in terms of an AR process is the very fact that you can invert this function. You can invert this characteristic polynomial, right? And that is what is invertibility. So the process by which you can write a MA process in terms of an AR process, the tool that you use to do that is invertibility. So invertibility is a property that, if satisfied, allows you to write a MA process in terms of a AR process.
Okay, thank you.
Does that make sense? Perfect. Good. So if you have any doubt, because this is a very important concept and generally it amounts to confusion, but it's good if you can, prepare a summary chart or something. I'll try to see if I can provide you guys with that. Maybe I'll just, provide it at the end of everything. Okay. So let us now see what happens if we generalize this. So now what we will look at is a moving average model of Q order. So again, MA of the order Q. So again, this MA process is really easy. And again, if you want to take, its covariance, it is going to be pretty straightforward because you will only have E terms to combine and none of the other terms. So again, if I were to write my moving average model with order Q, I can write it as, so I'm directly writing it using the backwards shift operator. So what I will have is something times ET, and I have here XT. So what I will have is 1 minus beta B plus beta. So this is beta 1, this is beta 2, and I will have B square up until beta Q and B raised to so I'll have B raised to Q there. So again, we have to remember that MA processes are always stationary. So what we have to now do is forget about making this process stationary. But still we'll try and figure out how to calculate the autocovariance for MA model. So would anyone like to assist me with that? Or let me just write it, I guess. Now it's pretty much the same thing that you're doing, again and again. So the more you practice this, the more it will, become habitual to you guys to calculate this autocovariances. So now what I'm doing is, instead of, or maybe we can try with that. So let us figure out gamma 0. So I have gamma 0 here. And if I were to write my gamma 0, what will it be? It will just be the covariance of xt times xt. And now I'm, ignoring the mu that I have here again, because in covariance, it really does not matter. And most of the times you assume, the mean to be 0. So it's just 0, or you subtract this mu here because you want the expectation of this thing to be 0. So if you take expectations on both the sides, you know that the answer that you get should be equal. And you know that the expectation of A is 0. So you know that the expectation of this side should also be 0. So if you do not have mu here, then the expectation of xt should be 0 for this to be a valid process. So these are just some nitty-gritties that you will eventually, get used to once you see more problems and see more questions. And then you see the pattern that goes on. So now I'm trying to figure out the covariance between this and that. So let me just rewrite this xt that I have up there. So I'm ignoring this mu for now, and I'm just writing that my xt is summation where, so let me just see what's there in the books. So they take g. Yeah, so we'll just take xt as summation of j going from 0 to q. And I will have beta j here times e t. So I have not written this in terms of the backwards operator. I have just written it in terms of the actual value that I will get once I multiply this b with et. Right? So if I multiply this b with et, what I will get is et minus 1, and that is with b1. So if I have et minus 0, I know that I should get here as coefficient 1. So I assume that my beta 0 is 1. And I write my xt as such. So now I'm again, instead of xt here, I will just substitute this. So xt I can write as, just 1 plus beta 1 et minus 1 plus beta 2 et minus 2, so on till beta q e t minus q. And what I'm doing is, I'm just taking a variance of this guy. So I square all of these, and I know that my covariance is going to be 0, right? And the variance of a constant is what? It is just so we will not have 1 there. We will have 1 times et. So I'm taking a variance of this guy. And what I will get is variance of et plus variance of beta 1 et minus 1, and so on. And if I write this, it's just sigma squared, and this is going to be just beta 1 square sigma square plus beta 2 square sigma square, and it goes on till beta q square sigma square Do you guys agree with this? Is this clear or is this making sense?
Yes.
Good. So now again I can just take sigma square as common and write that my answer for this is nothing but summation j going from 1 till 0 till q and beta j square, right? So this is my value for gamma 0. Does this make sense? So now let us try to figure out the value for gamma with any lag, which is unknown. So I'm trying to now figure out gamma k. It will just be covariance of xt, comma, x t plus k, right? Or t minus k. So let me just take x. Anything, you can take anything. So now I will have to figure out covariance. So I know that I can write my xt as such. So this will be summation j taking values from 0 till q beta j e t minus j. And for xt plus k, I will write summation I taking values from 0 to q. And now remember, instead of p, you will have t plus k. So wherever you have t, you will write t plus k. So beta I will be as it is, and e, instead of t, you write t plus k minus I. And now you are trying to figure out the covariance between these guys. So again, you have to consider the fact that only when the subscript for E here and the subscript for E here are same, this is going to take a value which is not equal to 0, right? So what I do is, I can just, rewrite it as, so I'm taking the summations outside and the covariance inside. So I have summation j going from 0 to q, summation I going from 0 to q, and then beta j and beta I, these are just constants. So these have come out, and I have a covariance of et minus j, comma, et plus k minus I. And now to figure out this covariance right here, what I will do is, only if t minus j is equal to t plus k minus I, which implies that only if my I is equal to j plus k, this covariance takes the value which is sigma square, otherwise 0. Okay, so now we ignore the terms where we get the answer of covariance as 0, and we only keep the cases where we have the answer as sigma square. So if I have an answer as sigma square to this, I know it does not depend either on I or j, so I can take it outside here. So, or maybe just, write it like this first. J going from 0. So now I know that if I'm writing this value of sigma square here, I'm already taking into consideration that my I takes values j plus k. So if I know that my I goes from 0 to q, what is the maximum value that j can have if I goes from 0 to q? So I know that j is what? J is just I minus k, and the maximum value for I is q. So the maximum value for j will be q minus k. So you have to take this change of limits into consideration. So remember, we did a similar thing in the AR process as well, right? And there we never cared about the limits. Why? Because if you go back and have a look at it, you had a sum which goes from 0 till infinite. So if you have both of these j's and i's summing up till infinite, you don't have to worry about the maximum limit on the sum, right? But here in this case, you have a limit which is q. So you know that your I can never take values beyond q. And if you input that, you also get that your j can never take values beyond q minus k. So this will just be q minus k here. And instead of I again, I'm going to write j plus k. So I have beta j here, and this will be beta j plus k. And this sigma square as it is. So I'll have sigma square, which can, be taken out because it is just a constant. So I know that my gamma k is nothing but sigma square summation j going from 0 to q minus k beta j times beta j plus k. So this is the final answer that I am looking for. But there is one more thing that we need to be sure of when I'm talking about this. So I know that if I have my value of k less than q, then and then only it makes any sense for me to calculate this autocovariance. Because if I'm looking at a lag which is greater than q, so let's say if I have p plus q plus 1 here, so my lag is indeed q plus 1. You know that this value will be 0 because there will be no common terms that you can find in these e's, and that will just be 0 then. So another important thing that we did here was to assume that beta 0 is 1. So you should never forget that. That is also important. Okay, and that is it about the MAQ model. So let us now try to figure out the ACF, the autocorrelation function, for some example of a MA process. So before we do that, let me just ask you guys a question. Is everything clear up until now? Do you guys have any questions about this process, MA process, or in fact AR process? So I will take that as a no. So let us have a look at an example. Okay, so we are given a process which is something like this. and you have to calculate the ACF. So till what lag can you calculate the ACF? Anyone?
2.
Why?
Because En minus 2 and Xn, so the difference is 2.
That is actually a good answer, but I asked a tricky question, so I can save you from that. So what I asked was, till what lag value can you calculate the value for ACF? So you can figure out ACF for any number of lag. It is just that it's going to be 0 after 2, right? Because what you're looking at is a MA2 process. So do you guys want to try this on your own? Or let me walk through this, but I guess
We can try.
yeah, I think you all can try. So I can give you guys some time to try. I think it's a good practice. Till then, I'll just, write the next question that you're planning to do. Oh, I should give you time to, copy this in your books. So yeah, just copy that in your books and I'll. Are you guys trying?
Ma'am, is there any condition to prove invertibility?
No, you don't have to prove anything. You just have to figure out the covariance and then the autocorrelation.
Okay.
So you use the same thing, the same kind of thing that we used previously, but instead of writing it in terms of, you will figure it out. Just try and write it. So the variance for my E is sigma, okay? Sigma square.
Ma'am, gamma 0 is 62 sigma square.
I got
Yes.
the same.
Yeah, that is correct.
Can you show the next question?
Okay, so did you just figure out gamma 0 or the other ones as well?
Gamma 1 is 35 sigma square and gamma 2 is 6 sigma square.
Gamma 1 is 35 or is it minus 35?
Minus 35.
Okay, good. And the other one is?
All others are 0. Gamma 2 and 3.
Gamma 2 is 0, you mean? Did you try? Gamma 2 cannot be 0,
6
right?
sigma square.
Yeah, it is 6 sigma square. Perfect. Okay, so the next question is this. Just write it down till I, write the answer for the previous question. I just feel like making this quiet. So we have to figure out if this process is invertible or not. So right? You have to just take the characteristic equation and see its roots. And there is some condition that each root must satisfy for it to be invertible. So I will just write. Is this clear to everyone?
Yes.
Good. So now try to figure out, if this process is invertible or not. Oh, so you can actually see arrow. So did anyone try? What was the characteristic equation that you have? What are the roots that you get for this equation?
Half and 1/3.
Half and 1/3, right? So if I were to write this, I would just write it like this. And I have 1/3, right? So now do you see, so remember the time when I wrote it as G, E, F and all those variables. So this is how it looks like. And we know that we have lambda is equals to 1/3 and 1/2. So what do you guys think? Is this process invertible or not?
I'm invertible
And why do you guys think, and why do you think it is invertible?
because the roots are strictly less than 1.
The roots are strictly less than 1. Okay. Okay, good. And what about others?
Yes, it is.
And others?
It is not invertible.
Why do you think so?
As we saw in AR process as well, the root should be greater than 1.
Okay, but why do you think that's gonna help you here?
Can you repeat the question you just said?
So my question is, now we have roots, right? So we know that all of these roots are less than 1. So is my MA process invertible or not?
It's not invertible because the root should be greater than 1 in magnitude.
Yeah, right. So because the roots are greater than 1 in magnitude, this process is not going to be an invertible process. So
Right.
remember, this is actually the confusion that each and every student has whenever they study time series for the first time. So you're not only the first person. So when I claimed that my roots should be less than 1, right? I claimed that my roots should be less than 1 for when? When I had already inverted this whole thing from here till there, right? And I wanted this to converge. So remember, the characteristic equation that I had was for the inverse of this, right? So now I am looking at the roots of something which is just this. Do you guys understand the difference? So this is very important. This characteristic equation that I have here is the expansion of inverse of this here, and the roots I want to be less than 1. But what I'm looking for in the question that I have is the roots of this equation right here, right? And that can, so if I'm looking at something here, I know that I'm not looking at its inverse. So if we take inverse of this and we figure out a characteristic equation for that, then the roots should be less than 1 in absolute value. But here, because we haven't yet inverted it, we want the roots to be greater than 1 in value. So, and here we know that these are less than 1. And therefore, this MA2 process is not invertible. Does this make sense? Please ask me if you haven't understood this concept, because this is actually the crux of, determining whether a process is invertible, whether a process is stationary. So you have to keep in mind what characteristic equation that you are looking at. Which equation is it that you are looking at? Is it the inverse or is it the actual equation? So if it is inverse, then you know that the roots should be less than 1. And if you are not taking its inverse, you know that the roots should be greater than 1, which is kind of the same thing that you have in AR. Is this clear to everyone?
Yes.
Should I move to the next model? So do let me know if you have any doubts within MA model now. I'm going to start off with the next model. Take that as a no. Okay, so now we will have a look at ARMA model. So I know that I have studied the autoregressive model and I have studied a moving average model. And what if sometimes the process that I'm looking at linearly depends not only on its own past values, but also on the combination of current and previous values of a white noise error term. So what I am looking for now is a ARMA model. And it has two orders, P and Q. And this combined determines the actual order of the ARMA model. So if I were to write ARMA model, I can write it as something. So I have xt here. And remember, I'll have lagged values of x itself till p. So remember, this is the AR's and this is the MA's order. Okay, so here I have alpha p x p minus mu. And again plus, I will have q terms for beta. But before that, I will also write et here. And now I will have beta 1 e t minus 1 plus beta 2 et minus 2, so on till beta q e t minus q. And that will be the way to write my ARMA model. And again, you can use the backward shift operator to rewrite this model as something like this. So what I will do is, I will take all of these x's values on the left hand side and I will keep these values on the right hand side. So what I will get is 1 minus, so I'll get something in the bracket and here I'm assuming xt minus mu again. So I'll have 1 minus alpha 1b minus alpha 2b square till alpha p b raised to p. Right? And for the right hand side, I will have something like 1 plus beta 1b plus so and so till beta q, again b raised to q with e. Does this make sense?
Yes, ma'am.
Yes.
Okay, so that is how I can, write my ARMA model. And remember, this is just a combination of AR as well as MA model. So again, sometimes what you do is, instead of writing all of these equations, you have some function which denotes this whole equation. So for AR term, you will use phi, which is a function of backward shift operator. And for the MA term, you will use theta. And this is how you denote these processes that you have here. Okay, so this is just a polynomial of degree p, and this is a polynomial of degree q here, right? So I guess that's clear about ARMA process. And again, so now if I have to see when will my ARMA process be a stationary process? What do you guys think should be the conditions for my ARMA process to be a stationary process? Anyone?
Same, the mean and variance should be constant.
Right, the mean and the variance should be constant. So if you look at the ARMA series, the way I have written it in the white, if you take the mean and if you take the variance, you see that all of these E terms that you have are just the MA process, and the mean is going to be 0 and variance is going to be sigma square with each of these coefficients squared, which is just a constant for all of them. Right? So what you figure out is you can again ignore the MA part in the ARMA process and just focus on the AR part. So if this characteristic equation satisfies the condition of stationarity, then you know that the ARMA process is also a stationary process, because we know that MA part is nevertheless going to be a stationary process. So you just need the roots of these characteristic equations to be greater than 1 in absolute terms, right? So now let us try to have a look at one example of an ARMA process. Oh, and also there is something that now you need to be careful of, right? So whenever we looked at the AR process, we saw that the PACF after P lags. So if you're looking at an AR process with order P, then the ACF after P lags still keeps on decreasing, and the PACF after P lags cuts to 0. But what happens with MA process is the opposite. The ACF of the MA process after Q is 0, but the PACF keeps declining geometrically. And if you have an ARMA process, we know that it is a combination of AR process and the MA process. So we expect that the ACF as well as the PACF, so none of those will cut off to 0. And that is where sometimes the difficulty comes, because you can never really see what will be the parameters of P and Q, right, for the AR and the MA process. But you know that your process at hand is some ARMA. So you can use ARMA to model the process that you have at hand. So let us now try to figure out the autocorrelation function for ARMA 1,1 process. So now I am saying that I have an ARMA process where my P is 1 and my Q is also 1. So what do you guys think I should write as xt? And I'm assuming that the mean of xt is 0. So I'll just write alpha xt minus 1. I don't have to write subscripts here because there is only one alpha which I have. And again, I will write et plus beta et minus 1. Is this clear? So now I have to figure out the autocorrelation. And we know that before we figure out autocorrelation, it's always easier to figure out the autocovariance. So let us try to do that. So the very first thing that we should do is figure out the covariance of xt with itself. And when we do that, we are looking at gamma 0, right? So I can just rewrite this again. And what I'll have is alpha xt minus 1 plus et plus beta et minus 1. And again, I have some alpha xt minus 1 plus et plus beta et minus 1. And if I were to expand this, what I will have is alpha square covariance of xt minus 1 comma xt minus 1 plus. So now I'm trying to figure out the covariance of this with that. So I took this with this first And now I will take this with that, and I know ET with XT. ET minus 1 with XT is always going to give me 0. So I just write 0 plus 0. And now again, do you guys agree that this should be 0? So what I have written here is covariance of ET comma XT minus 1. And what I have here is the covariance of beta ET minus 1 comma alpha XT minus 1. Do you guys think that these should be 0 or not? Well, let us try to figure out what's the answer. So let me just burst it. It's not 0. Because I can clearly see, right? If I expand my XT minus 1 here, I can get my ET as well, right? So let us just try to have a look. Or not, right? So wait, where is my equation? It's here. So I have XT minus 1. So if I expand XT minus 1, I will get XT minus 2 here. And I will have ET minus 1 and ET minus 2 here, which has nothing to do with ET. And here, I have beta ET minus 1. So if I am looking at XT minus 1, then I will have ET minus 1 here. So this term in XT minus 1 should be correlated with this term here. So this guy, isn't it going to be 0? But not this guy. So let us try to figure out this value. So I'll have covariance of beta ET minus 1 comma, and instead of alpha XT minus 1, let me just take this alpha here. And now I just have XT minus 1 inside. So if I expand XT minus 1 here, I will get alpha times XT minus 2 plus ET minus 1, which will be correlated with this, plus beta ET minus 2, which will not be correlated with this. So I know that the answer that I have for this is alpha sigma square. So instead of 0 here, you will have...
Shouldn't it be alpha beta sigma square because of the beta as well?
Oh, yeah, thank you very much. So this should be alpha beta sigma square, right?
Right.
Okay, good. So remember always, do not take any of these covariances of XT with ET at face value. Always try to figure out those, and that will always, guide you much better. Okay, so good. Let us solve what comes ahead. So that's done. And now we have done this with that, and this with that. So now we will do ET. And I know that ET is going to only correlate with the same ET here. So what will I have here again? Some sigma square. Right? I will just have some sigma square because this will be covariance of ET, comma ET, which is sigma square. And then ET with beta ET minus 1 is going to be 0 again. But I will again have to check my correlation of ET with XT minus 1, which I already know is 0. So I should maybe have written here plus 0, plus sigma square plus 0. And now again I have this term beta ET minus 1. So again, we have to take this with that. What do you guys think I should have there? I will again have this term, right? Alpha beta sigma square, because I have this beta ET minus 1 with alpha XT minus 1. So I'll have alpha, beta, sigma square, and if I do et minus 1 with et, it's 0 again. And for the last term, what I will have is this with that. So that will just be beta square, sigma square. Is this clear to everyone?
Yes, ma'am.
Good. So now if I were to rearrange all of this, so I will just, rewrite this equation here. So I have gamma 0, and I have covariance of xt minus 1 with xt minus 1, which is what? Gamma square, gamma 0. So I can take this here and again write it as gamma 0, and this is equal to alpha beta sigma square plus alpha beta sigma square will be 2 alpha beta sigma square. So I have 1 sigma square which I can take as common, and I will have 1 plus 2 alpha beta plus beta square, right? So now I can write my gamma 0 as sigma square upon 1 minus alpha square times 1 plus 2 alpha beta plus beta square, right? Does this make sense to everyone? Any doubts with this? So you could have also used, the covariance plus the variance one, but I have just resorted to multiplying this with that again and again till the end. So yeah, this is the answer that you have for gamma 0. Now let us try to see what happens with gamma 1. So now we have to figure out the covariance of xt. So again, let me ask, what should I take here, xt plus 1 or xt minus 1?
Minus 1.
Minus 1, right? Because I have minus 1 in the expansion of xt. So I'm more likely to get a nice answer with xt minus 1. Yeah. So what I have for xt comma xt minus 1 is, I can again, just rewrite my xt here. So what I will have is, so remember, this is another method that I'm showing you guys now to calculate the same covariance. So you can use any method that you want to figure out the covariance as long as it satisfies all the properties and the rules of statistics. So now I'm replacing my xt with alpha xt minus 1 plus et plus beta et minus 1. Comma xt minus 1. And now I'm just rewriting this as alpha times covariance of xt minus 1 comma xt minus 1 plus. So now I will have the covariance of et with xt minus 1. So covariance of et with xt minus 1 and beta times covariance of et minus 1 comma xt minus 1. So remember, this is nothing but just gamma 1 and this is alpha gamma 0 plus. So now what is the answer that I have for covariance of et comma xt minus 1?
0.
It is going 0, right? It is just 0. And for this guy, I will have beta times sigma square. This will just be sigma square, right? So my, just give me a minute. Okay, so now what I have here is a gamma 1 which takes value alpha times gamma 0 plus beta times sigma square. And now I already know the value for gamma 0, which I can easily substitute in here to figure out the value of my gamma 1. And if you do that, you will get something like this. That's it. And now let us try to figure out what happens if you have a simple lag k instead of 1 or 2. So gamma k. This will be covariance of xt with x t minus k. And I can just rewrite that. Again, I'm just directly doing this step. So I hope you all are used to this by now. So this will just be alpha times covariance of xt here minus 1 and x t minus k plus covariance of et comma xt minus k plus beta times the covariance of et minus 1 and x t minus k. And remember, this we are doing for all the values of k which are greater than 1. So for 2, 3 and so on. Okay. So now I know that this is going to just be what? Alpha times gamma k minus 1, right? And now I have covariance of et comma x t minus k. So if I have with et any x with the subscript
k minus 1 or k plus 1?
It will be t minus k minus of this thing, right? So it will be minus k plus 1. So it can, so if you, maybe I can, so here it's going to be t minus
Okay, got
minus t minus 1, right? And this is just equal to gamma minus k plus 1, which is equal to gamma k minus 1, as this is an even function. Good. So that's clear now. So now, can someone tell me the value for this? So I have to figure out this value for all the values of k which are higher than 1. So I know that
0.
even if I have 1 here, it's going to be 0. So for anything even greater than 1, it's going to be 0. Perfect. And now what will be the value here? So I have t minus 1 and there I have x t minus k. So if you look at the lag, so let us just substitute 2 there. What will you have? There will be a lag of 1, right? And whenever you have a lag of 1, the value is just 0. So for this case, again it's going to be 0. Not only for lag 1, but also for any lag which is higher than 1. So you know that the value for gamma k that you have is just alpha times gamma k minus 1. So this seems a bit like, a recursive equation. that we have at hand with us. So what you can do is, you can substitute in here again and again. So you can write this as alpha times alpha gamma k minus 2, which can be, just alpha squared gamma k minus 2. And if you go on to do the same thing again and again, what you will end up is if you have here, right, yep. So here you will have alpha k minus 1 with gamma subscript as 1. So you know that this 2 always adds up with this to give you k. So k minus 1 plus 1 is again k here. So you know that you can write gamma k as this for k greater than 1. Is this clear?
Yes, ma'am.
Good. And this is like, yeah, this was actually a question where you were supposed to prove all of this stuff. But yeah, we just did that. So I think I'll end today's class here itself. And I would encourage you all to, not do anything, but just to revise whatever I have done up until now. Because I'll have another class tomorrow. So tomorrow I will just go through another kind of a model where if you don't start with a stationary model initially, then what is it that you can do to make a model stationary? And we will have a look at that model. It's called ARMA model. And before that, we will solve one question related to ARMA model, maybe, maybe not. And then I'll see whether I should start with a new chapter or maybe we can go through one of the past exam questions because I think time series requires that practice. So we can maybe, because next chapter is not much of solving. It's much of understanding the theory and the process of how do you go about time series when you meet it in practice. Which I guess I can, even if I start it on Sunday, I should be able to finish off with that by Monday. So yeah.
I have a question actually.
Yeah.
This alpha k is equal to, gamma k is equal to alpha raised to k minus 1 into alpha 1 can also be written as alpha gamma k is equal to alpha raised to k gamma 0, right?
Yes. And why don't you do that? Can you answer that?
Why don't you do that? As I'm a little confused by what you mean by that.
So I'm saying, why you shouldn't want to do that is just because, we have defined that we are trying to write this for k greater than 1. So alpha k minus 1 seems like, a possible thing to start off with. But yeah, if you write it as gamma k equals to alpha raised to k times gamma 0, that's also equally correct. If you were asked to show that, then you could have easily, shown that as well. I mean, just one more step. You're correct.
Okay. I just asked because that would just include the value of k as also sort of being equal to 0 or equal to 1. If that, because here it's strictly greater than 1, which is why I was asking.
Yeah. So actually, this I
can be
took this
greater than
from,
equal to 1 also, right? Because if k is equal to 1, then gamma 1 is effectively equal to gamma 1, right?
Wait, what?
For the value which is saying where it says for k greater than 1, it can also be k greater than equal to 1, right?
Yeah. It will be just alpha raised to 0. So what you will get is just, gamma 1 equals to gamma 1. So that wouldn't make much sense, right? So you already have a nice value for gamma 1 here, right?
Right,
So
right.
if you
But I was just
substitute,
asking it for sort of like uniformity in the formula, so that
yeah.
it's applicable
Yeah.
for other values of k as well.
Yeah, so
Even
see, it is applicable. It is applicable, but what you have here is a nice value for gamma 1 in terms of alpha, beta, and sigma square, which are just constants, right? And if you
Right.
substitute here k as 1, you will get this 0 and you will get gamma 1 equal to gamma 1, which wouldn't give you anything. So what you do is you evaluate gamma 1 from here, and then for all of the other cases, instead of going through all of this process again, which might prove difficult, you have this nice equation where you just have to substitute the value of gamma 1 and raise this alpha to the power k minus 1 to figure out any gamma k.
Got it.
Got it? Okay,
Yes.
good. That was actually a very good question. So, any more doubts?
No.